So the next little proof strategy that we're going to talk about is a proof by cases. And I've actually used this in previous videos before, but I thought it'd be good to pull this out individually and sort of formalize it. So what is a proof by cases? Well, in general, a proof by case proceeds as follows. Let's say that you want to prove some statement like, for every x p of x. Then a proof by case would proceed as follows. The very first thing that you do is you split it up into cases covering all possible values that x can take. That's why it's called a proof by cases. Next, you handle each one of those cases individually. And this is the important part, don't miss this. The whole point behind a proof by cases is that you want to split the values that x can take into cases that are more convenient to handle. So for example, if you were to split it up into some cases where in one case you can use one proof technique, in another case you can use a different kind of proof technique. Whereas if you consider all the cases together, then it would be much more difficult. So that's the whole idea behind this strategy is let's split up our space of the values that x can take and handle them individually. And we split it up in such a way that it's more convenient to handle. So I think this is best illustrated with an example. So let's consider the following. So here, I want to show that 27 is not the square of a natural number. So it is one of these universal quantifier statements. I'm saying for every n, a natural number, n squared does not equal 27. And that is my propositional function p. And so if I wanted to split it up into cases, there's a bunch of different ways that I could do this. So, well, I could be kind of stupid and I could split it up into case 1, n equals 1, case 2, n equals 2, case 3, n equals 3. That's actually not going to work because there's infinitely many cases. So I have to be a little bit more clever about how I'm going to split up my cases. So I'm going to split up my cases in the following way. So first off, I'm going to consider natural numbers n that are between 1 and 5. That's my first case. My second case is going to be let n be greater than or equal to 6. So you'll notice that for the natural numbers that I'm talking about, these two cases cover all possible natural numbers. And that was important. We had to split up our cases into ones that handle every single value that x can take. And indeed, in this case, these are all the possible values that natural numbers can take. So I split it up into these two cases, and we will see in a second why I did this, because it is more convenient. So the second step is we have to handle each case individually. So I'm going to start with case 1. So I'm going to take this inequality right here, and I'm trying to show that 27 is not the square of a natural number, so it's pretty natural to think of taking this inequality and going ahead and squaring it. So if I were to square this entire inequality, I would get 1 squared, which is just 1, is less than or equal to n squared is less than or equal to 25. Well, notice 25 right here is less than 27. So there's no way that any number between 1 and 5, when you square it, it becomes 27. And that case is now finished. I know that for any value of n between 1 and 5, if I square it, I'm not going to get 27. So now let's go ahead and consider case 2. And so for case 2, here now, n is greater than or equal to 6. Well, let's see if that same trick that we did just before in case 1 also works here. So I took this inequality and I squared it. And now check this out. N squared is greater than or equal to 36. And that is strictly greater than 27. So we know that for any n that is greater than or equal to 6, its square cannot equal 27. And this has finished my proof. I have covered all possible natural numbers, those between 1 and 5 and those greater than or equal to 6, and considering each of these cases individually has allowed me to conclude that n squared is never going to equal 27. 27 is not going to be the square of any natural number. The whole reason why I split it up into these couple of different cases is in this case, we're showing that the number is less than 27. And in this case, we're showing that the number is greater than 27. If I were to combine these two cases together, then I wouldn't have been able to use the strategy of just squaring both sides, because sometimes it'd be less than 27, sometimes it'd be greater than 27, and I wouldn't be able to make any sort of conclusion. So these two cases were convenient for me to be able to use this proof technique of simply squaring these inequalities. That basically is the idea behind a proof by cases.